Okay, so when we're reaching back into our memory to try to remember these, when we have it in this function notation, if we add or subtract something to the x value, what kind of shift is that? Horizontal. Okay, so this is a horizontal shift. Okay, now remember when it is grouped with the x, we always do the opposite. So if we had x plus n, we think opposite. So what's the opposite of a positive n? Negative n. So this would send us left in units. Did you remember that?
I did remember that.
Okay, so if we had x minus n, we always think opposite when it's grouped with the x. That would shift it right in units. It does make sense if I give you an equation. Okay. If I give you just a function, it doesn't. All right. So, this f of x, doesn't f of x, can't we substitute y in for that when we're thinking about it? The value of the function is your y value. So this makes sense. This says, hey, I'm going to take the y's and add or subtract something to my y's. So what kind of shift would that be?
Vertical shift.
Vertical shift.
Up or down and
And this happens in the same way. So if I had f of x plus n, this would be up in units. And if I had f of x minus n, that tells me to shift down in units. Okay, were you able to get all of this without me?
yes.
Yes, ma'am.
Okay, so mostly yeses, but then some no's. That's good. But does it make sense now?
Yes.
Okay, good. All right, reflection. We have two kinds of reflections. We can reflect over the x-axis or the y-axis. Those are the two types of reflections we study. You can actually reflect over lots of different things, but the two that we're going to work on are reflections over the x and the y. All right, just looking at this, this negative is out in front of the entire function. Well, if we think of f of x being the y value, doesn't this look like it changes the y's to the opposite?
Mm-hmm.
And if we change the y to the opposite, the point 1, 2 would go to the point 1, negative 2. What does that reflect it over? Good. This is a reflection over the x-axis. Okay. Now this one looks exactly like it. This says take your x's and do the opposite. Well, if we take our x's and do the opposite, what kind of reflection will that be? A reflection over the y. And we change all the x's to the opposite. Okay, scale changes. We have two types of scale changes. One is where we affect the function vertically. We can vertically stretch it, or we can vertically compress it. And your teachers may have used the word shrink. Then we could affect it horizontally. We could horizontally stretch the function or horizontally compress the function. Now, when we look at this here, this is when there is a coefficient to our function, when our function is multiplied by a scale factor. Doesn't this, if I thought of it this way, look like, hey, I'm multiplying my y's by something? So that is going to affect my function vertically. This is a vertical scale change. And it's a vertical stretch. I'm going to divide it up here. It's a vertical stretch when my a is greater than 1. And it's a vertical compression or shrink, you may use it either term, when that multiplier is between 0 and 1. Okay, now, do you see how the a on this one is inside affecting the x? Well, if we affect the x, that's going to change something horizontally. So this will be either a horizontal stretch or compression. And when it affects the x, when it's grouped with the x, we kind of have to think of it opposite. So our horizontal stretch occurs when A is actually less than 1. Because anytime it affects the x, we always do the opposite. So what is if A were 1/2, what is the opposite of multiplying by a half? Multiplying by 2. Do you see how that would stretch it out if I took all my x values and multiplied it by 2? Makes them bigger, stretches out my function. All right, so it's called compression when that multiplier is greater than 1. And I'll give you an example with real numbers in a minute so that it actually makes a little more sense. Okay, I'd like you to take these rules and see what you can do in this function. And the way, if I were you, the way I would start it is I would say, okay, what are the important points on here? Well, if I had a point here, a point here, a point here, a point here, I could quickly sketch in that shape, this function. So, take this, let's look at A. What does A tell us to do to this parent function? If this is y equals f of x, tell me in words, what does this tell me to do? Shift down 4 units. So take each one of these points and drop it down 4. Okay, what does B tell us to do here?
Shift right 3.
Thank you. Shift every point right 3. Okay, go ahead and finish up A through H, because I think that's why I had only one person answer my last question. No, I already did. Go ahead and finish A through H. If you're watching the video, you can fast forward until you see something change on the screen.
Double the x's.
It's the x.
You double the x.
Half of x.
Double.
So that means it's
You
gonna
double them. You double them.
Connor's correct.
Why would you double the x?
Anytime it's grouped with the X, you always do the opposite. Now, I'm going to show you
Serious?
this. We're going to add an example right here. Go back to my sentence and just
I remember that.
So did you do it from the beginning or from the one before?
So we do you do like stretches first and then move the graph. I can't remember. Like for age.
because this is vertical and this is horizontal, the order doesn't matter.
Okay.
But I would think of it like PEMDAS. I'm going to start inside these parentheses.
Okay.
So I'm going to do that shift first, and then I'm going to do.
Okay.
Does the line still just go out at the end?
Yeah. But what if they were like you're doing like moving it and like
You do that
vertical?
with PEMDAS. You start inside parentheses, and then you would do multiplication, and then you would do.
Okay.
Do you do it from the original one or
Everything from the original.
I get it. I get it now.
One, two, three, four.
Yeah, yeah.
know, we would move this graph, which is this one, right 1. Let's talk about y. The vertex of this one is at 0, 0. But if I plug in 0, do you see how it gets shifted? Left 1 and I square it, and it would give me 1. If I plug in 1, 1 minus this is 0, and 0 squared. Do you see how it takes the opposite of this is what becomes my vertex?
Okay. So why is if you have one axis, but that's only if it's on the if it's squared. Like, but what if it's not always square? Like, what if it's y?
If it's anything, if it's cubed, it does the same thing. If it's absolute value, it works the same way. I mean, you could try lots of different types of functions, and they all do this.
I hate that. Trabajo de calculadora.
That's Spanish 3.
Pretty easy. Yeah. We're still on predator birds. We've basically just done a review. Honestly, most of the time when I go to class, I just go in there and just kind of like sit in there and talk to the girl next to me, do the worksheets that she gives us, and talk to her in Spanish.
Why, if you talk in English, you get points on your grade?
I mean,
You're
she
probably not
says-
allowed to talk in English.
Yeah, she says she'll give us a ticket if we talk in English, and like every time you get a ticket, you get a point off of like your daily grade or something.
Which Spanish is that?
Everyone knows that.
3.
But it's like it's really easy. Plus, I talk in English to her all the time. She gives me a ticket. Most of the time, it's like after like a whole bunch of failed attempts at Spanish, I'm just sitting there looking at her clueless because she'll go on and try to like. Because I'll like ask her a question about something, and she'll like try to give me like a detailed explanation of like the origins of.
Okay, so let's take a look at these. And in A, do you see we have f of x minus 4? So how would we say that in words? That translates, or it's a shift down 4 units. So we take each of these points in our parent graph over on the far left. We take each of those points and shift them down 4, and that's how we get the graph for A. For B, given this notation, that shifts the function right 3 units. So we take every point on our parent graph on the left and shift it right 3 units, and that gives us our new graph. Now, C says y equals f of negative x. There's a negative changing all the x's. When we change all the x's to the opposite, how would we describe that transformation? It's a, what is it? Reflection over the y. So C is a reflection over the y. Does it look like from this one to this one that I reflected it over the y? Yeah. D. We have f of, in parentheses, 1/2 x. F of half x. So if it affects the x, we always do the opposite. The opposite of multiplying by half is multiplying by 2. So we take each of these x values and multiply them by 2. It is a horizontal stretch by a scale factor of 2. E, we took the whole function and did it left 2. F, we have a composition of transformations. We shifted right 1 and down 2. G, there's a negative out in front, which gives us the reflection over the x, and then we shift up 3. So a reflection over the x-axis, and then shift up 3 units. H, we shift left 3 units, and then the 2 out in front of the function that doubles our y's, we would call that a vertical stretch by a scale factor of 2. Any questions on part 2? Go ahead and make any corrections if you need to. Now, the bottom, which I see some of you have already done, is asking us to come up with the equation for the transformation. Can you write the rule for the transformation? So on the far left of your paper, you have the parent function. And I want you to look at A, B, C, and D and see if you can write the rule for the transformation. How is it shifting? And all of these are just shifts. There's no reflections or stretches or decompressions.
I do have real bindings and stuff. I use this for this class. There's no public club to get anything back. And I can put books in it and stuff like that. Better. If I wanted to bind it, I'd have to get like a 3-inch to hold like 6 of these. Or I could just get this to hold like 2 of these and old paper forever. I'm piloting the system.
Yeah.
Only downside is it's starting to get torn up.
They sell those made out of plastic.
Do you think really? I need to get on them. I really like them. I would use these for other classes because it's easy. Or at least classes where I have like a lot of workbooks and stuff. But my parents just have like a big school supply bin. And I thought I would test it out because I knew that we get a lot of workbooks. So it's working for me so far. Let's see how corners hold up.
Okay, let's do a check. Did you get for A, did you notice it was shifted left 3 and down 2? So f of x equals x plus 3, because we always do the opposite, and then minus 2. B, it was shifted right 1 and up 2, so we do the opposite here, f of x minus 1 plus 2. This was shifted left 2 and down 5, so f of x plus 2, do the opposite, minus 5. And this was shifted right 1 and down 2, so it's f of x minus 1 minus 2. Did those make sense? Great. All right, now we're going to talk about the specific function we're going to focus on this year. Last year we did linear and we did exponential. This year, we're adding my favorite one, the quadratic. F of x equals x squared. You guys could have told me that was named quadratic, couldn't you? Because what's the degree? 2. So this is a quadratic function. Now, last year, I used this function in class, but we didn't really call it a quadratic function. But that's what it is. We use this as an example. A quadratic function looks like a parabola that opens straight up or straight down. And we're on the back of your worksheet now. Now, a quadratic is a squaring function. Call it a squaring function because it takes my input, my domain, and does what to it?
It squares
It to get my output, my range. So a quadratic is a squaring function. And that's where this table came from. If we take these inputs and plug them into our function, we get these outputs. 0 squared is 0. Negative 1 squared is 1. Negative 2 squared is 4. Negative 3 squared is 9. Positive 1 squared is 1. Positive 2 squared is 4. And positive 3 squared is 9. And if we plot these points, we get this shape. And this is our quadratic function that's open. This is our parent graph.
Miss Willoughby, can't you make that kind of on the TI-36 probe?
This is a screenshot. And yes, you can make that table. I don't want us to make this table because we can square numbers in our head pretty easy. We don't need to take time to do that. If you had an ugly, messed up function, yes, there is a way to do that. And I can show you in just a minute, okay?
I know, but aren't there like a couple other functions? I can't remember some of the names of them, but
There's a lot of functions we'll study. All right, so this is our quadratic function. And if this is my parent graph, f of x equals x squared, we're going to take that parent and shift it. We're going to take this parent and stretch it or compress it and reflect it. So now we're going to focus just on the quadratic, just on this function. So this one says, take that quadratic. How do I know? Because I have this 2. And what am I going to do with this parent graph?
To the right.
Shift it to the right too. Now, the point I just shifted was the point that was at 0, 0. That point is called the vertex of this quadratic function. The vertex is either going to be the lowest point, the minimum, or the highest point, the maximum. So it just depends on how the quadratic opens. So this is our vertex, and that's what I'll start by shifting. Now, instead of coming up with this table every time, I want us to think of this as being a squaring function. This function is squared. So if I took my input, if I went 1 unit to the right, 1 unit to the right, what is 1 squared? 1. So if I went 1 unit right, I'd go up 1. If I went 2 units to the right, what is 2 squared?
4.
4. I'd go up 4. If I went 1 unit to the left, what is negative 1 squared?
1.
1. And if I went 2 units to the left, what is negative 2 squared?
4.
4. And do you see I've just found enough points to make a nice shape for my quadratic function? I am not very good at this on the Moby, I'll go ahead and tell you. So my parabolas are not going to look as good as yours. Okay, so we just graphed this using what we know about transformations. Did we have to make a table? No. If you graphed it the old-fashioned way by making a table, you'd pick points for x, plug them in, subtract 2, and then square it and get out points for y. But this is quicker, because I don't have to figure out where the vertex is. I know exactly where it is. It got shifted right 2 units. What happens to the vertex on B? Where is it shifted? Up 3 units. 1, 2, 3. So now this is my starting point. Yes, ma'am. Oh, I'm sorry. I meant to tell y'all. Please change that to a 2. That's a typo.
Oh, I was getting worried.
That's a typo.
Thank goodness.
Oopsie. I'm so glad y'all have good eyes still. All right, so this is shifted up 3 units. And now that we've corrected it, it's a quadratic, so it's a squaring. So if I go 1 unit to the right, 1 squared is 1. 2 units to the right, 2 squared is 4. Slightly off the graph. 1 unit to the left, negative 1 squared is 1. 2 units to the left, negative 2 squared is 4. And now I have a nice graph of the function. I always start my moves from the vertex. When I talk about moves, I'm not talking about points. I'm talking about how do I move from the vertex. If I moved 1 unit to the right from the vertex, 1 squared is 1. I'd go up 1 unit. If I move 2 units to the right from the vertex, I go up 4. Where do I shift my vertex to? Left 2, down 1. Okay, so if I went to the right 1 unit, what is 1 squared? 1. If I went to the right 2 units, what is 2 squared? 4. If I go to the left 1 unit, 1 squared is 1. To the left 2 units, 2 squared is 4. And then I have my quadratic. Now, some of you may not be buying into this transformation thing. So let's just test. If I plugged 0 for my x into this function, if I plug 0, I get 0 plus 2, which is 2. 2 squared is 4. 4 minus 1 is 3. Did I have a point at 0, 3? I did. If I plug negative 1 into this function, negative 1 plus 2 is 1. 1 squared is 1. 1 minus 1 is 0. At negative 1, do I have negative 1, 0?
Yes, you did.
Yeah. So do you see how it works? Could we make a chart? Sure. But this is a lot quicker. A lot quicker. Okay. Let's look at this one. Tell me where the vertex shifts on D. Left 4. 1, 2, 3, 4. So we're going to start off there. Now, this one's different. This one has my first reflection. Now, a negative out in front of the entire function. Out in front of the entire function. Does that affect the x or the y?
Both.
This is the y's.
Oh, yes.
Because this is like negative f of x. Here's my function. And negative out in front changes the y's to the opposite. So instead of going right 1 and down 1, up 1, I'm going to go right 1 and down 1. Instead of right 2 and up 4, I'm going to go right 2 and down 4. Because this negative flips it over the x-axis. So reflection over the x. So if I had to describe this transformation, I would say it's a shift left 4 units and a reflection over the x-axis. Okay. This one. This one is different than the one I'm going to add. Do you see how on this one, the 1/2 is multiplied out in front of the x squared? And on this one, the 1/2 is actually being squared with the x. So this one causes a vertical compression. This one is going to cause something horizontally, and we'll do that one in just a second. So this one's going to shift up 2, 1, 2. Start right here. The negative is going to tell us instead of going over 1 and up 1, we're going over and down. But then what does the 1/2 do? Instead of going over 1 and down 1, we're going to go over 1 and down 1/2. Instead of going over 2 and down 4, we're going to go over 2 and down 2. And the same thing happens on the other side. At this point, have you noticed that all of these have been symmetric? There's an axis of symmetry that goes through the vertex. Okay, now sometimes it's hard to figure out where a fraction goes. So since we know we're taking half of things, what are numbers that we can square and take half of easily? Well, 2 squared is 4. We can take half of that, can't we? And then 4 squared is 16. What's half of 16?
8.
So if I went over 1, 2, 3, 4, I could go down 8. So if you'd rather jump to that one so that you have this nice, easy to follow path here, pick numbers you can take half of. Okay? Okay. You didn't have this one. You can watch this if you want to. Is it shifted at all? No. But this is affecting the x. So instead of 1, 1, we double the x. We go over 2 and up 1. Instead of 2, 4, we'll go over 4 and up 4. And before I go any further, let's make sure this makes sense. If I plugged 2 in for x, what's half of 2? 1. And what's 1 squared? Was there a point at 2, 1? Yeah. Do you see I have a point at 4, 4? So if I plugged in 4 for x, what's half of 4?
2.
2. And what's 2 squared?
4.
4. Did that prove that what we're doing is correct?
Yes.
Yeah.
So it does.
So this would be a horizontal stretch, because what we're really doing is multiplying our x's by 2, aren't we? It's a horizontal stretch by a scale factor of 2. Even though it looks like a 1/2 right here, what we're really doing is multiplying our x's by 2. All right. Now, I would like you to try graphing f all by yourself, and then we'll talk about all the characteristics. Check your graph with my graph. Did you put the vertex at 1, -8? Did you go over 1 and up 2 because of this vertical stretch by a factor of 2? And over 2 instead of up 4, we went up 8 because we had to double that y. So this shifts it right 1, down 8.
Yeah, I get the vertex. I don't get the vertical stretch.
Okay, the 2 is multiplied out in front, and when it's out in front of the function, it doubles the function part, the y part. So instead of going over 1 up 1, we double that y part. We go over 1 up 2. Yeah.
I'm kind of confused.
I just
Because I plugged into. I got the first thing and then I changed it because it looked wrong. I'm so confused. I'm confused.
I just
the
plugged
outcome
in all
of
the
graph
numbers.
because
That made a
all
lot of
like
sense.
You plug the points into the graph.
Yeah.
Okay, that is another way to do it. And when you would do that, you would always start by finding your vertex first and then plugging in numbers that are on either side of your vertex.
That's what I did.
If you just, that is another way to do it.
so they have
My
to be,
way is quicker.
They have to be on
Your way's
either
quicker.
side of your vertex.
I plug in stuff.
That's where I went.
It has to be on either side of the vertex.
Wait, no, I plugged in two.
Okay, if you're doing by plugging into the function instead of doing the move. I don't know that you realize you're making
Yeah,
me
Miss
laugh.
Willoughby, if you plug in 2, then you get -4.
No, you don't. If you plug in 2,
Yes, you do.
2 minus, oh yeah,
Yeah, 2 minus 1 is 1 times 2 is 2, squared is 4, minus 8 is -4.
Yeah, she's square then.
No, you have to multiply by
PEMDAS,
2
dog.
first.
parentheses.
Parentheses, so then you square.
Then multiply.
Choose the exponent, and then
That's x minus 1.
Yeah. No. The 2 in front, you multiply by the 2 in
no,
front.
you do what's in.
Then you
No,
square.
PEMDAS says we have to square it first. And then you multiply times 2. Yeah. Why don't you just do it the way I
So you got 2, well then still, 2 minus 1 squared, that would be 1 times 2 would be 2.
2, and 2 minus 8 is 6, which is where my point is. That point right there is at 2, negative 6. So even if you do it by plugging in points, you should get the same thing. But because it's a squaring function, if I move right 1, squared is 1. But because of the 2, I double that, up 2. Right 2, 2 squared is 4. But because of the 2, I double that and go up 8.
I mean, that's what I had in the beginning, and I just get confused by when you have like 30 numbers and just
Okay, one with you in just a second. All right, domain. Do you see that this is going left forever and right forever as it goes up? That it's getting wider and wider and wider and wider at the top? So it is going forever left and forever right. So my domain would be from negative infinity to positive infinity.
How do you know when to use parentheses and brackets?
Okay, let's talk about that. We use parentheses if it does not include the number. We use brackets if it does include that value. Now, since infinity is a concept, it's not a number, we can never really get to infinity, so we can't include it.
Okay.
So when you deal with infinity, you will never have the brackets, because we can't get there. Now the
Is like
range.
infinity to 4 though, the side with the 4 would have the bracket on it, correct? Okay.
So now let's do the range. So for domain and range, we always go least to greatest value. So on range, we're doing the lowest y value to the greatest, the least to the greatest. Well, this one has a minimum y value right here. What is it? Negative 8. Does it include the negative 8? Yes. So since it includes it, I'll use the bracket. So it's from negative 8 to infinity. Now, if you were taking a standardized test, they would probably write this. The range is all the y values that are greater than equal to negative 8. Do you know that these two mean the same thing? Okay, good. So if this were a multiple choice standardized test, like the end of course test, they probably won't write our answer in interval notation like we expect you guys to do because you're in accelerated. They're probably going to have it in inequality notation. So just be advised that they'll have the answers like that. Okay, x and y intercepts. Well, we can see them clearly on our graph, can't we? The x-intercepts are negative 1, 0, and 3, 0. And the y-intercept is 0, negative 6. Now, what if I didn't have this nice graph and I just had this equation? Do you guys remember that to find the x-intercepts, we could just plug in 0 for y? Yeah. If we plugged in 0 for y, we get 0 equals 2 times x minus 1 squared minus 8. So I would add 8 to both sides. I would divide by 2. I would take the square root. And I would add 1. What is 2 plus 1?
3.
3.
Wow.
What is 1 minus 2? Negative 1. I should have said 1 plus 2. 1 plus 2, because this is what it is. 1 plus or minus 2 equals x. 1 plus 2 is the 3. 1 minus 2 is the negative 1. Do you see how we could do it algebraically? How would we find the y-intercept algebraically? Plug 0 in for x. So we get f of x, which means the same as y, equals 2 times 0 minus 1 squared minus 8. So I'd get 2 times 1 minus 8 is negative 6. Is that what we got? Yeah. So even if we didn't have the nice graph, we could find our intercepts algebraically. All right. Now let's do intervals of increase and decrease. Now, some of you, I taught you how to do this. Others learned from different teachers. and some of you may not have learned this at all, so I want to go over this kind of slowly. We are looking at this function, and we want to talk about where the function increases from left to right and where it decreases from left to right. So if I started here on the left side of this, and I headed right across the function, what is this function doing first? Decreasing. So it is decreasing from negative infinity to this 1, isn't it? And then after the 1, what starts happening? It's increasing. So if we look at this, there is a decreasing interval from negative infinity to the 1, and then it increases from 1 to infinity. And we're talking about what happens as we travel from left to right. So we have to use our x's, don't we? Because the increasing and decreasing is describing the up and down, the y part.
You don't use
So
brackets when you're talking about the interval of increase.
It's not wrong to use the brackets, but I don't, because I consider this the point where it switches.
Okay.
For me, I can't go, this is included here or included there. Now, some textbooks use the brackets. Most of them use the parentheses. You can use either, and I won't count it wrong.
Okay.
All right, in behavior, what happens as we approach negative infinity? This function is increasing. As we approach positive infinity, this function is increasing. So we would describe the in behavior as x approaches negative infinity. The function, and you could use f of x or y, approaches positive infinity. And as x approaches positive infinity, the function also approaches positive infinity. Now, when I was looking at your summer work, those of you that had accelerated coordinate algebra in middle school, you flip-flop these. You said y approaches positive infinity as x approaches negative infinity. Completely acceptable. That's fine. It's the same thing. Okay?
Do you have to put the positive in front of infinity? Or can you just write infinity?
No, you don't have to. All right, let's look at these two. Over what intervals is the function positive and is the function negative? Okay, if I am looking at positive and negative, the x-axis differentiates where the function is positive and negative, doesn't it? Above the x-axis is positive. Below the x-axis is negative. So I'm going to finish these notes on my website for you tonight. Your homework is out of your workbook. It's 1 through 4, 6, 7, and 9. But on 1 through 4, I want all these characteristics. I'm going to put up the video if you need to hear them. I will also post the notes. Okay. So over what interval is the function positive? So if we look at this, above the x-axis is where our function is positive. So this is positive from infinity to that 1. And again, from 3 to infinity. This function is negative when it falls below the x-axis. All the y values are negative there. So this function is negative over the interval negative 1 to 3. So it is positive from negative infinity to negative 1 and positive from 3 to infinity. It is negative from negative 1 to 3. Is there a max or min? Yes. This point, the vertex, will always be either a max or min on a quadratic function. So yes, we do have a min here. And at what point does that occur? It's the same as the vertex, 1, negative 8. So the vertex is also that point, 1, negative 8. And is there an axis of symmetry? Yes, there is an axis of symmetry. The axis of symmetry is the vertical line that passes through the vertex. And if we look carefully at this, we could fold the quadratic over this line and it would
be symmetric to itself. So since it's a line, it is x equals, and it is x equals 1.